is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through curve sketching. So I need to be able to give you a polynomial and you need to be able to sketch the curve. So what you'll need to do is find its y-intercept, easy, x-intercepts, and turning points and concavity. Now, you can use your graphics calculator to help you. You can use your graphics calculator to get the x-intercepts and the y-intercept, and you can use it to tell you the answers for number 3, but you will need to be able to show and justify your working out why the turning points are what they are. So let's go ahead and graph fx equals, and I'll put this in factorized form, x plus 1 cubed times x plus 6. So this will be a quartic. So our first step is to identify the y-intercept. Well, that's easy. You just let x equal 0 for that. So if I let x equal 0 in this expression here, I get 1 cubed times 6. I get y equals 6. So the y-intercept is 6. So for the x-intercepts, you let y equal 0. Now, when it's factorized like this, it's really easy. We use the null factor law. Either the first bracket equals 0 or the second bracket equals 0. If it's not factorized, remember you can just graph it on your graphics calculator and then use the calculator menu. And then you go to 0 because intercepts, x-intercepts, are known as the zeros of this function. So don't need to do polynomial long division or anything like that. All right, the bulk of the work's going to come in through calculating the turning points and concavity. So you can use your graphics calculator to cheat a little bit and find out what they are, but we need to justify by hand. So to find the turning points, remember we find where the first derivative is equal to 0. Then we find the values at the second derivative to determine whether it's a maximum, minimum, or turning point. Using the second derivative will also tell us about concavity. So let's differentiate this. So we could expand this and differentiate term by term, but it's probably a bit easier to use the product rule. So remember the product rule, you differentiate the first. So to differentiate this, you're actually using the chain rule, power to the front, decrease the power by 1. And remember you times by the derivative of what's in the brackets, but of course the derivative of what's in the brackets is 1. So that's derivative of the first times the second. And then we add the first times the derivative of the second. So this is the first, but the derivative of the second here, it's just 1. So using the product rule, this would be the derivative. Now to make this easy for ourselves, note that both have a factor of x plus 1 squared. So I can move that x plus 1 squared out the front. So what do I times by x plus 1 squared to get the first thing? Well, that's 3 lots of x plus 6. And what do I times by x plus 1 squared to get this? Well, I need to times it by another x plus 1. So now we'll just expand this to make it a bit easier. So the derivative is x plus 1 squared. And when I expand the brackets and collect like terms, I get 4x plus 19. So if the first derivative equals 0, either the first bracket equals 0 or the second bracket equals 0. So 4x plus 19 equals 0, x is minus 4.75. So substituting those in to the original equation here to find out what the y value is, I have minus 1, 0. And if x equals minus 4.75, y is about minus 65.9. So now I'm going to calculate the second derivative. It will help me classify these points as minimum, maximum, or inflection point, and it will also tell me about concavity. So I'm going to differentiate this here, and again, I'm going to use the product rule. So I take the derivative of the first and multiply by the second, and then I add the first times the derivative of the second. So the first times the derivative of the second, well, the derivative of the second, 4x plus 19 is just 4, and I get this. So what I'm going to do is factorize this both have a factor of 2. Both have a common factor of x plus 1. I'm going to do that to make things a little easier. So here I've just factorized this here to make things a little easier. And then I'm now going to expand the brackets and collect like terms in this second bracket. That will make things even easier. So it'll be 2 outside of x plus 1, and I get 6x plus 21 in the second bracket. Okay, so what does this tell us? How does it help? Well, from this, I know that if I substitute x equals minus 1 into this expression here, I'll just get 0. So that tells me that minus 1, 0 is actually an inflection point. Now, if I were to substitute x is minus 4.75 into the second derivative, so I'm substituting it into the second derivative here, I actually get a positive number. And that tells me that x equals minus 4.75, this stationary point here, is a minimum. Now, one other thing I can get from this, because I factorize it like this, the second derivative will be 0 when x is minus 1, or when this bracket here equals 0, which means x is minus 3.5. So x equals minus 3.5 wasn't a stationary point, but because it makes the second derivative equal to 0, it is an inflection point. So at x equals minus 3.5, there is a non-stationary point of inflection. You don't have to use this, but it might make the graphing easier. All right, let's turn all of this into a graph. So I know I've got a y-intercept of 6 and that the lowest turning point, the minimum turning point, minus 65.9. So I'm going to draw that down here. So note my y-axis doesn't have to be exactly to scale, and I don't need to label 1, 2, 3, minus 1, minus 2, all the way down to minus 65.9. But I do need to label the important points. So I've labeled here for the y-intercept and here for a turning point. So we know that the x-intercepts occur at minus 1 and minus 6. So we'll have 1 here and 1 here. The turning point of minus 4.75 minus 65.9 will be around this area here. So when x is minus 3.5, if I substitute it in here, I get like y is minus 39.06. So if you want to include that point, that will be about minus 3.5 minus 39.06 will be about there. So we have everything we need to draw the graph. So what will happen, it will come through the x-intercept there down towards its minimum turning point, stop and turn around. And see now it's concave up. At this non-stationary inflection point, it will now change to being concave down, so it'll look more like a frowny face. So we'll look like a frowny face. It will hit this point. This is a point of inflection. That is minus 1, 0 is a point of inflection, and it's stationary, so it will then change concavity again. It will go back up to looking like a smiley face, and it will go through the intercept like that. So that is the graph of fx. It does take a lot of effort, I understand, but please make sure you work through carefully and methodically. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.